All right, so lesson 17.3 is about the ozone layer and how we have harmed it and how we have fixed it actually, or done a lot to make it better. And just to state again is that the ozone layer and the hole in the ozone layer and all that is not global warming. Sometimes those two things get confused, but they are not related actually. So back to ozone. Remember that ozone is found in the troposphere and the stratosphere. The troposphere being the layer closest to Earth that we breathe, and the stratosphere is the layer right above it. And ozone is super beneficial in the stratosphere. It shields the Earth's surface from harmful UV radiation from the sun. And the ozone molecules there are not super dense. There isn't a ton of them, but they're so successful or efficient at their job that it helps protect life on Earth. If we didn't have these, then our DNA would be constantly undergoing mutations from the sun's harmful radiation. Think of it as a really, really, really good can of sunblock. And what happens if you don't have that? Remember that ozone in the troposphere is bad. It's bad. But in the because that extra oxygen can break off and cause damage to our cells. But in the stratosphere, it's good. And then back in the 80s, scientists discovered that chemicals that humans have made that we used in everyday things were causing ozone depleting substances that were causing the degradation of the ozone layer. And the way that we responded as a race, as humans, to solve this problem stands as one of the society's most successful efforts to address a major environmental issue. All the compounds that are affecting the ozone layer are human-made, they're synthetic, and the primary ozone depleting substances are called halocarbons. And these are human-made compounds that come from hydrocarbons, so long chains of carbons and hydrogens, where some hydrogen atoms have been replaced by halogens from the periodic table, specifically chlorine, fluorine, or bromine. So one specific class of these halocarbons is chlorofluorocarbons, CFCs, and they were discovered and made in the 70s for use in refrigerators, fire extinguishers, propellants for spray cans like aerosol, like hairspray, and cleaners for electronics. And scientists noticed that CFCs very rarely react with other chemicals, so they thought they would be harmless for humans and for the environment. But because they're so non-reactive, they're super non-reactive in the troposphere, which means that they get successfully to the stratosphere and then they start breaking down. What happens is they are broken down by the UV radiation from the sunlight. And so here's a CFC. They would get broken down into where that says that on there. The chlorines would break off. And the carbons would go elsewhere. The chlorines would break off. And then what happens is the chlorines will go and find an ozone layer. They'll steal one of the oxygens away from the ozone. So the ozone becomes just oxygen, which is the gas that we breathe. And then the ozone layer the ozone molecule no longer exists. And the bad thing about this is that the chlorine will then reset itself and do it over and over and over again. So it's going to split a lot of molecules. Each chlorine can free 100,000 ozone molecules because it has a very high residence time in the in the stratosphere. So it's bad. It just goes around and around and around, getting rid of ozone molecules and turning them into oxygen, which is not good. And so because of this, there is an ozone hole over Antarctica that appears every spring in Antarctica, which is September our time. So they realized in around 85 that an area of thinned ozone concentration called the ozone hole was forming every spring over Antarctica. And so what happens is high altitude polar stratospheric clouds containing nitric acid were breaking down CFCs into chlorine, which was then being released in the spring when the sun broke up in the clouds. So basically every winter, so June to August in Antarctica, these super, super heavy clouds in the stratosphere had nitric acid in them, and they start breaking down the CFCs into chlorine. But the clouds are super heavy and there's a polar vortex that keeps them all there. And so they just sit there in the winter. Suddenly in the spring, they're released as the clouds break up. So around September, they go into the atmosphere and start depleting the ozone. And the solar radiation that they get as they move into spring speeds up the process and speeds up the ozone depletion. The hole is there until December when the winds have finally gone, the polar vortex has left, and now suddenly the winds are mixing with wind from other areas, so the ozone depleted air is spreading out and ozone rich air is moving in. So every spring there's this big hole, and scientists were concerned that the elevated UV levels could promote skin cancer and damage plant life, so they were really worried about it. And so what humans did to fix this is we came up with this treaty called the Montreal Protocol, and it's an international treaty. It came out in 1987, and it was signed by many countries around the world. And basically, it did a lot of things like agreeing to cut, or countries that signed it agreed to cut CFC production in half by 1998. And since then, there have been a lot of additions to it, or additional agreements. And these were things like deepening the cuts, so cutting down CFC production even more, speeding up the timetables for compliance, and adding new chemicals to the list that were ozone depleting substances. So you can see that this is ozone destroying potential from all substances. So all substances that were in the stratosphere. And so this is what would have happened with no protocol. So it was rising like crazy. Then in 1987, we released this. This was the Montreal Protocol, would have lowered it, London Protocol, and then Copenhagen and Beijing. So we've had lots of rules, and now it's lower than it was then. So it has really been successful. So by phasing out and replacing these chemicals, we've stabilized the ozone hole. So now basically all industries have replaced these CFCs, or ozone depleting substances, with different chemicals that will work just as effectively. So we've mostly halted the advance of ozone depletion and stopped the ozone hole from worsening. The ozone hole is expected to fully recover sometime after the year 2060. The reason that it's going to take so long is because there's still of the 5.5 million tons of CFCs that were in the stratosphere, most of them are still there because they have such a long residence time. So there's still going to be a lot more ozone broken down, but we are no longer increasing it. And so by the year 2060, hopefully we'll have recovered fully. And the Montreal Protocol is now considered to be a model for solving global environmental problems. It was successful for a number of reasons. The first is that informative scientific research developed rapidly, facilitated by new and evolving technologies. Policymakers engaged industry in helping to solve the problem. So the governments went to the industries and said, we need to work on something else. What can you use instead of CFCs? And the industries were willing to develop replacement chemicals, in part because patents on CFCs were running out and firms wanted to position themselves to profit from next generation chemicals. And lastly, implementation of the Montreal Protocol after 1987 followed an adaptive management approach, adjusting strategies in response to new scientific information, technological advances, and economic data. So it was definitely a resounding success.